Good afternoon and welcome to today's webcast titled Model My Watershed, a Tool for Resource Management. This webcast is sponsored by EPA's Watershed Academy and EPA's Office of Wetlands, Oceans, and Watersheds, also known as OWOW. I am Ann Weinberg with EPA's Watershed Academy, and I will be moderating today's webcast. Thank you all for joining us today. We will start by going over a few housekeeping items. First, I'd like to briefly summarize some of the features of today's webcast. We hope you'll have a lot of questions, and please type your question in the questions box on your control panel and click send. If the control panel is not showing, simply click on the small orange box with the right arrow to expand it. If you have any problems viewing the broadcast, just let us know in the questions box also, and we will post an answer in that same box. The webcast will be archived for later viewing on EPA's Watershed Academy webcast page at www.epa.gov/Watershed Academy. And a PDF copy of the slides is also posted on the Watershed Academy website. Participants are eligible to receive a certificate for their attendance at the end of the webcast, and directions for obtaining this certificate will be presented at the conclusion of the presentations. And the materials in this webcast have been reviewed by U.S. EPA staff for technical accuracy. However, the views of the speakers and the speakers' organization are their own and do not necessarily reflect those of U.S. EPA. Mention of commercial enterprises, products, or publications does not mean that U.S. EPA endorses them. Now that we have completed our housekeeping discussion, we will kick off today's webcast. This webcast will provide a background on the Model My Watershed tool. The speakers will provide a demonstration of the tool, and they will highlight how this tool is being used by several states and others for their total maximum daily load TMDL program, their non-point source program, and municipal stormwater programs. Let me first introduce our highly esteemed speakers. Today we will hear from first Dr. Anthony Aufdenkampe. He is a senior environmental scientist at LimnoTech in Minnesota. He is the project manager for Model My Watershed at Stroud Water Research Center in Pennsylvania. Second, we will hear from Barry M. Evans, who is a senior research associate at Penn State University and also an adjunct faculty member at the Stroud Water Research Center. He is the author of the Watershed model that has been incorporated into the Model My Watershed online tool. And finally, we will hear from Bill Brown, who is the chief of the TMDL development section at Pennsylvania's Department of Environmental Protection. For their full bios, please see the webcast flyer on the Watershed Academy website. And a thank you to all of our speakers for joining us today. And one final note, before we kick off our presentations, we will try to answer as many questions as possible throughout the webcast. We will pose questions to each speaker after their presentation, and if time permits, we'll take any remaining questions at the end. However, due to the high number of participants, I think we've broken records today, not all questions will be answered, so please do contact the speaker after the webcast if you still want to follow up. The speaker's contact information is on one of our final slides. And with that, we'll begin our presentation. I will now turn it over to Dr. Anthony Aufdenkampe, who will give an overview of what we are going to cover in the webcast, first of all, and will then provide an overview and demonstration of the Model My Watershed tool. The floor is yours. Take it away, Anthony.
Thank you, Ann, for that nice introduction, and thank you to EPA for hosting this webinar today. We're the Model My Watershed and Wiki Watershed team. We're very excited to be presenting this to all of you. So there are four main sections to today's talk, and I'll be tag teaming with the co-presenters, Barry Evans and Bill Brown. I'll start off the presentation by giving an introduction to Wiki Watershed, the vision behind it and its history, and the motivation for creating the Model My Watershed web application, which we'll be demonstrating extensively today. I'll describe some of the funding behind the present project and then move on to a demonstration of some of the capabilities of the online Model My Watershed web app including the site store model and the microsite store model. I'll finish the first section by running through two different case studies of the site store model, and then I'll hand things over. Then I'll be open to questions, and after a short question period on those topics, we'll hand things over to Barry Evans and Bill Brown to discuss the multi-year watershed model functions within Model My Watershed. They'll go through an introduction and a history of the model components under that application and present 3 case studies, several of which have been utilized in Pennsylvania. And then finally, and after that period, they'll answer some questions about that section. And then we'll wrap up with a short section where I'll be presenting a bit of information about where Wiki Watershed and the Model My Watershed web app are heading into the future with immediate funding in hand, and also what the potential is long-term down the road. So with that, I'll first introduce the Model My Watershed project team. The Model My Watershed project was envisioned while I was a research scientist at the Stroud Water Research Center, and I owe a lot of those early envisioning sessions and current activities are still maintained by the Stroud Water Research Center. The Stroud Center owns the trademarking for Model My Watershed and Wiki Watershed, and we'll talk more about that at the very end. But the project from the very beginning has been a multi-institutional, multidisciplinary collaboration. I've since moved to LimnoTech, and I'm leading the technical development, but my colleagues Dave Arscott, Melinda Daniels, Steve Curlin, Tara Munson are overseeing the main body of the project. We've been working with academics and professionals such as Barry Evans, who will present the second half of the conversation, but then also with software engineers at Xavier and academics from Utah State University and University of Washington who have developed a lot of the algorithms behind Model My Watershed, and that collaboration is extending to include colleagues at Drexel University. We also have some work for educational end users or an educational audience, and we've done that in collaboration with Nanette Markham-Dietrich and Carolyn Stout from Millersville University and the Concord Consortium, respectively. We've received project support starting in 2009 from the National Science Foundation, and most recently and most extensively support from the William Penn Foundation. None of this could have gotten started without very early seed money from the Stroud Water Research Center, the Virginia Wellington Cabot Foundation, the Dansko Foundation, and then personal donations from Peter Kellerp and Mandy Cabot. So we thank all of those for the support of this work. So with that, I will move into describing kind of where this project started from. What was the vision? At the Stroud Water Research Center, there's a strong belief that information and knowledge about our water resources are critical for the future of water protection. And this idea of information and knowledge are the foundations of a functional democracy, I think, was Thomas Jefferson. So we realized, well, informing the citizenry about our water resources is therefore key to protecting our water resources. However, at the present, well, back in 2006 when we were first envisioning this, and I would say less so today, but still it continues to be a challenge to get a complete picture of the information and data from dozens of federal, state, municipal, academic, and volunteer sources who are all working on monitoring and protecting water resources within a watershed. There's been a lot of progress in the last decade, but challenges are still there. So that was the vision. In 2006, Google Earth, in late 2006, I think it was October, Google Earth came out for the first time, and that transformed the way which the public, students, and researchers looked at the Earth. Even researchers with GIS experience were blown away at how easy it was to look anywhere on Earth with high resolution at what was there. And a lot of really good science happened, while at the same time students and the public were enthralled by being able to look at their backyards. Around that same time, Wikipedia, there was an article in the journal Nature that that stated that Wikipedia had a lower error rate than the Encyclopedia Britannica. So there's still an urban legend now that, you know, people are messing with Wikipedia and there's nothing can be trusted on Wikipedia, but it's been over a decade since that myth was debunked by a study in the journal Nature. Essentially, crowdsourcing information really works if it's done well. And also at around that time, Facebook was really kicking off from being this tiny little interesting startup to being an important part of the way people communicated in our society, and now it's expanded even further. So the idea was, can we harness these three different capabilities of the modern web, internet and web, Wikipedia, Facebook, and Google Earth, to bring people together to share information about water resources? That question resulted in us developing the vision for what we call the Wiki Watershed. And we envisioned it as a set of web tools to support citizens, conservation practitioners, municipal decision makers, researchers, educators, and students. Now that's a really broad audience. We really believed that just like Google Earth and Facebook, that citizens and students could exchange knowledge with researchers and professionals in a productive way that was beneficial for all, and that a single platform could really serve a multiple of users. Because we believed that it was really only in this way that we could collaboratively advance knowledge in the way Wikipedia does. But specifically, we wanted to do this to target the end goal of enhancing stewardship of fresh water. From the beginning, we envisioned Wiki Watershed to have three programs. The first one, our flagship program, is Model My Watershed, which is what we're going to spend most of today talking about. It's a web application that we envisioned and have now developed to analyze real land cover data, real soils data, and other geospatial data to model stormwater runoff, water quality, and this is the most important capability, to enable the comparison of different scenarios of conservation or development in a real watershed in your backyard, so that this wasn't just some hypothetical tool that you could play with. Another component was Monitor My Watershed, which has been an envisioned web app until just a month ago when the William Penn Foundation funded us to move this forward. I'll talk a little bit about that, where we will develop interactive map-based discovery and visualization and sharing of water quality data from multiple sources. Right now, these capabilities are out there for different organizations and sources, and the data science has proceeded far enough that the data can all be aggregated into single applications, and so we want to harness that. We also are going to add resources to assist citizens to monitor their watersheds using low-cost monitoring approaches that are based on sound science. And we have a spin-off project called EnviroDIY that is about do-it-yourself environmental monitoring and science to help citizens and non-engineers and non-professionals and even professionals have low-cost approaches to monitoring so that we can expand our monitoring. And then lastly, we have envisioned an application that has a lot of social networking capabilities to try to develop a community of practice around the protection of watersheds and engage citizens with policymakers. The Model My Watershed web application is fundamentally a decision support system for water conservation, and you'll see us demonstrate that. We wanted it to be to allow really rapid visualization of watershed data. Model My Watershed is primarily about geospatial data, and Monitor My Watershed is primarily about water quality monitoring data. But all of this is important. So, and there are means to rapidly visualize it. We wanted to put at the hands of anybody high-performance geospatial analysis capabilities. Presently, geospatial analysis requires sophisticated software like ArcGIS or even an open source package like QGIS. Installing it and getting those things to work often has a cost in money and time that most individuals aren't willing to put forth to gather that information. Well, that's just to install the software for the analysis. Then on top of that, there's actually the gathering of the information. And we believe that that gathering effort is a really significant hurdle even for professionals to do a quick what-if scenario that might allow them to make quick decisions, or at least to prototype their ideas before moving on to the professional software packages. And then lastly, we wanted to put science-based predictions, basically real professional models that are used by professionals every day across the country. We want to put those in the hands of anyone with a web browser so that they can predict the impacts of human activities on stormwater runoff and water quality. The key is an intuitive user interface, just like Google Earth or Google Maps or Facebook or any of these other web applications. So an intuitive user interface that's familiar to people, that's obvious, and that provides a satisfying experience from any web browser, meaning that it performs well, it does what you expect it to do. We wanted it to also be easy to share modeling scenarios, because that's the key. We want to develop a community. So, and we're also envisioning with Monitor My Watershed the ability to easily share monitoring data. And as mentioned before, we believe that it is possible to develop features that are both useful and interesting for the public, citizens, students starting in middle school, and professionals. The initial funding for Model My Watershed was funded by the National Science Foundation's directorate for the Education Directorate, and it was really to ask the question, can geospatial analysis be taught in secondary school? And the evaluation at the end of that project, that first phase of funding, that little pilot project, was that this application was equally useful in a middle school classroom, in a high school classroom, and in an undergraduate classroom. And now we know of it being taught for modules in graduate classes. So the latest round of money and what's driving a lot of the work now and a lot of the development is funding from the William Penn Foundation's Delaware River Watershed Initiative. I guess I'm jumping ahead here in the slides. The William Penn Foundation has put into place over $60 million since 2014, and they're planning for a second phase of money. They have very deep resources to initiate some relatively impressive, very impressive amount of conservation efforts. They explicitly engaged a large number of regional and national conservation organizations to protect tens of thousands of acres of land and actually implement conservation best management practices. They also wanted to test various innovative approaches and monitor the results over time, so that information can be gained to do it better in the next round. So here we have a number of the organizations that are involved, and the present Model My Watershed web application has been developed very much with them in mind. Many of these are NGOs with staff, and so the NGO staff member that's implementing conservation practices is one of the end users that we're specifically targeting. So this is where I'm going to actually open up the Model My Watershed web app and show you a little bit about its data visualization and analysis capabilities. So I'm going to switch over here to my web browser. There is a Wiki Watershed web page, and I'll just mention this very briefly. As I mentioned, Watershed has Model My Watershed as the flagship tool. You can launch the app from here and also find out more information and documentation about Watershed. There are other models in the toolkit. I mentioned Monitor My Watershed. I mentioned the microsite runoff model. I mentioned Enviro DIY. And then there are some other things that we're bringing into the mix from previous work. All of this is supported by the Stroud Water Research Center. So when you click on Launch the app for Model My Watershed, this is what you see. You see a map of the United States. It looks pretty straightforward. It looks really simple, but there's a lot of power under the hood that we're going to explore today. One of the first capabilities is that we have the entire NHD plus medium resolution stream network for the continental United States enabled under the hood. All the flow lines and all the other attributes under the hood here. We have also the USGS National Land Cover Database for the entire United States and the USDA GSIRGL Soils Database under the hood, in addition to some other layers which I'll discuss maybe in a little bit of detail further on. You'll hear more about some of these. So we have a lot of data right at one's fingertips, and if we zoom in to any given area, I can also change the transparency of my images, and I can also change the base map to any number of base maps, either from Google or Esri. So I'm going to zoom in to a little bit my backyard, the city of Minneapolis. That looks like a reasonable scale right there. Whoops, went in a little too far. And I'm going to change to satellite with roads. Actually, at this scale, I'll stick on terrain and jack up the land cover database. What is under the hood here is a lot more information which one can analyze, and I'm going to demonstrate that by selecting an area of interest. That's the first step in any of the work that we do in the Model My Watershed web app, is selecting an area of interest. And there are 3 different ways to select that area of interest. We're going to go over those. But the most impressive one is the free draw. And I'm just going to select a chunk here of North and South Minneapolis with some rural areas, where I just free drawed on the map an area of interest that's 1,300 square kilometers. And what immediately kicked off here was an analysis of the geospatial information within that area of interest. That analysis tells me, so right now we're looking at the NLCD data over the Google Earth terrain map, and here we have a summary of what fraction or how many square kilometers of that area are in each of the NLCD land use classifications, the 16 primary ones. We also have the ability to look at the soils data. Unfortunately, we have to click on the map and the analysis tab separately right now, but we are in nonstop development, and that's actually a feature that we plan on fixing within the next 6 weeks. Or I should say improving. So here you can see the NLCD data for that area. Urban areas don't actually have USGS GSIRGL data associated with them. Urban areas don't have soil classifications. In this area, we also have some estimates for the animal populations, and Barry Evans is going to talk a little bit more on that. That's from USDA farm animal populations by county, and this is an interpolation. We have the NPDES permitted point sources, which actually, surprisingly enough, because of the sewer districts, there are no point sources in that area of interest. We'll look at those later, but those get listed on the map. And then this last water quality tab is actually for the Delaware River Basin only. I'll talk about that at the very end of the presentation, that one of the things that we do is kind of more customized customization. We have the ability to add regional customizations, and I'll show you an example of that here. I'm just going to do a really quick analysis to see if I can pick up some point sources so I can show you how that feature works. Okay, here we go. So here we have, looks like 5 NPDES point sources with a little bit of information. The numbers that are presented in the table and in the pop-up balloon are the average annual loads and discharge from each of these point sources as obtained from the EPA discharge monitoring reports. So you can see how quick and easy it is to get an idea of what's going on in a watershed. So from there, I did my web demo, and we're going to move on to looking at how to do a site storm model and what exactly the site storm model is. When we were in the last page, you might have noticed that right next to the Analyze button, or the Analysis tab of that side panel, was also a big modeling button. So I'm going to tell you a little bit about what's under the hood there, and then I'm going to demonstrate it. So the site storm model has a number of core components. First of all, it's simulating a hypothetical 24-hour storm. So it's not gathering any real weather data, but rather it's doing what a lot of engineers do, is to say, okay, well, let's plan for the 2-year flood, the 10-year flood, the 50-year flood, the 100-year flood, whatever. So if you have a flood frequency table, you can find out exactly how much rainfall is usually associated with each of those floods, and you can dial that number in. And I'll show you exactly how that works. And then from there, our runoff model figures out how much water, how that water from that precipitation event will get distributed between infiltration, runoff, and then a small amount going to evapotranspiration. The runoff model is a hybrid model that runs the algorithms behind SLAM, or the Source Loading Management Model for Windows. That's a set of algorithms for urban small storm hydrology that was developed by Robert Pitt and is presently within the WinSLAM program. WinSLAM is a very popular stormwater management tool that is proprietary. A lot of civil engineers use it for calculating how to design stormwater features. SLAM itself actually defaults to TR55 in rural areas or in really large storms. The algorithms were developed for small storms. TR55 can handle very large storms. So we picked the algorithms out of the WinSLAM manual and coded them into the package. In addition, we have some very basic water quality estimates that we got from EPA's spreadsheet tool for estimating pollutant load, or STEP-L. The STEP-L program is available for download from EPA, and it's a spreadsheet from which we can fetch the algorithms that were used, and it was relatively straightforward to program those in. And in addition, the site storm model, we've developed the ability to create scenarios and compare them for the what if a land cover change happened, either for the better or worse, or what if we installed some conservation practices or best management practices, BMPs. What if BMPs were implemented on the watershed? So with that, I'm going to go to the case study number 1. And this is an open case study. I'd like the audience to type into their question box some ideas for some small city in the United States. Give me a city name and a state that it's located in, and I'll zoom to it and do a little modeling where I'm going to just very quickly mock up. So type those into your question box on GoToMeeting, and the organizers will give me one to choose.
We have many, Anthony, but Syracuse, New York was the first one, or Charlottesville, Virginia. Those are the first two out of the box.
Thank you. Okay. So I'm going to reset where I was before, and we're going to do a full reset. Actually, I don't have to zoom out to the country. I can, how do you spell Syracuse? I should know.
S-Y-R-A-C-U-S-E.
Thank you. Thank you. I knew there was a Y in there. Okay. So we'll go to Syracuse, New York, and we will pick the National Land Cover Database. We're going to change the base map to satellite with roads so that we can see a little bit better what we're looking at here. I'm going to dial down the transparency a little bit. And all right, I see some interesting areas over here. How about in this area right here? So I'm going to zoom in and to this little kind of city block, and I'm going to do a free draw and say, let's say there was a plan there was some planning going on with the water inputs to this stream here from this neighborhood. And let me turn all those off. We can change the transparency of the NLCD to see how the National Land Cover Database maps out the land use in these areas. We can see what that distribution is. We can see what the distribution of is the soils, whether or not we have any point sources. We don't. That's unfortunate. That's always fun to throw in. And now we can model it. So I'm going to click on the model, and I have two choices here. I mentioned earlier there are two choices for models. The site storm model is designed for single 24-hour storms and primarily for small sites, although it's performant enough that you can run it on large watersheds, but the algorithms weren't really designed for that. I'm going to click on that, and when I click on that, you can see that I immediately get kicked into this modeling pane where the model looks at the current land use and the current soils. I can always go back to be reminded of what was there, and using that bit of information, it calculates for this 2.5 centimeter or 1 inch storm, how much of that will go off as, how much of it might get infiltrated, how much of it might come off as runoff, and how much of it might be expected to be evapotranspirated. I can change the size of the storm. Let's make this a big storm. This is a 6-inch storm or a 15-centimeter storm, approximately. There we go. And now it's rerunning the model and recalculating the partitioning of that rainfall. And you can see a much larger percent of that rainfall then goes to runoff. What's happening under the hood here is a geospatial calculation over every 30-meter pixel in this area, which is approximately 1 square kilometer. I can get a more precise number. Actually, I can't. I forgot about that in this model output. All right. So, oh, I forgot to show the water quality tab. So this is what EPA Step L calculates would be the load and the loading rate for that storm. Loading rate is the total load for that area divided by the hectare. So this is and it would be an apples-to-apples comparison. And then what might be an average concentration. There's no stream routing in here, so this could be considered the load to the nearest surface stream. There's no routing involved. So what's most interesting about Model My Watershed isn't just this ability to look at what the current conditions are. And I just saved the model you might have seen here, but I also have the ability to create scenarios. And I have my current condition tab, which is always calculated, but I also have this new scenario tab. I'm just going to name this scenario Dev1 or for a development scenario, and I'm going to say, well, maybe what's going on here is that there was, some application to build to take this forest lot and turn it into a commercial mall with a high residential or kind of maybe a residential housing development on the back side of it or something along those lines. And you can see that I'm just drawing in these different changes to land use. It's recalculating the model as I draw in the land use changes. Those modifications are stored here with some area estimates. And I have a new set of model outputs. I can add an additional scenario, and I could call this a conservation scenario. I'm going to call that conservation 1. And here I'm going to say, well, you know, maybe there's a, what would happen if we take this the other way? What would happen if we implemented some kind of really nice best management practice conservation scenario in this area, like cluster housing? What if we actually decided to plant some forest over here where it looks like there's some bare earth? I may be getting that wrong, but we're going to convert those land uses into forest and do a bunch of tree planting along the roads, let's say, and to change that land use. And let's see here. There's a high school in here. We'll zoom into this high school. And let's put some green roofs on the high school. You can do this work at very high resolution. It looks like I cut off that high school in my haste, but you get the picture. And I could put in more green roofs over the rest of this area. So I do that. So I've got my green roofs, and I'll put in porous pavement over here in these parking lots. All right, I'm going to cover up a school and pretend it's a parking lot. But anyways, I put in a nice porous pavement parking lot, and I've got those modifications. You might have noticed right above the modifications, there's a compare button. The compare button allows me to do an apples-to-apples comparison of what my current land use conditions are with my development scenario and my conservation scenario. It's apples to apples because it resets the precipitation to be equal for all of them. I can quickly see how these different scenarios that I developed compare to each other. And we also run a 100% forested scenario to try to mimic the pre-human natural state to give an idea of what would happen there. And so you can see some relatively large differences between these scenarios, and I can dial in a larger storm. It's still calculating. Nothing is updated yet. You can see that happening here to give us an idea of how, you know, what happens on a natural landscape. We still get runoff during large storms in natural landscapes. And I can change this to all look at water quality. So I'm going to go back to look at this, and I want to just mention that these calculations that are happening under the hood here are happening for every single 30-meter pixel along these lines. And what I clicked on was a link to the site storm model, which is an educational tool that uses the exact same model algorithms. And it basically says, here's a parcel of land that has a single land cover and a single hydrological soil group with its different infiltration rates. These are straight from USDA and USGS, these specifications. These are real land, these are real geospatial data, as I said before. And I can change the size of the storm, and it immediately models very rapidly how the partitioning is between infiltration, runoff, and evapotranspiration. So for a forest, I can change the hydrological soil group and get different amounts of infiltration. This is the model. It's just the model on a place where the land use and the hydrological soil group are equal to each other. So it's a unique combination of these two things. So it's more than a pixel. It's a group of pixels that share that commonality. That's what's running under the hood here, and we can run this at thousands of square kilometers, but really it's meant for smaller spaces. So with that, I'm going to move to case study B, which is a conservation planning, which is a real-world preliminary conservation planning scenario that happened for the Delaware River Basin Initiative in Pennsylvania. So I'm going to hop over here to another tab. Oh, here we go. So this was modeled up by one of my colleagues at the Stroud Water Research Center, and this is a property, a land parcel that was traced, in which a conservation organization was wondering what would be the water quality benefits to taking these agricultural fields and replanting them, and basically conserving this area under conservation easement, turning this into green space, replanting them into forests and meadows. So they drew up what this would look like, and you can zoom in a little bit to see what that would be like, and compare the model outputs. And you can see that for that property, the runoff for a 1-inch storm, or here I'll go to a 2-inch storm by comparison, something that happens about once a year, you can see that the benefits are actually quite substantial to that conservation work. If we look at the water quality, I think we can see that there's a very substantial improvement in the suspended sediment load. These numbers are actually showing negative numbers, and that's what happens when you have an uncalibrated model, I guess. So there's some substantially improved benefits for the water quality modeling. So with that, and so what happened then was that the NGO who was proposing that took that information. They were using it to evaluate multiple sites, is my understanding, and then they took that information and said, okay, this is a property worth investing in. Let's put a little bit more money into some real planning using desktop GIS, and I think they then took it onto the Mapshed model, which is a desktop GIS and watershed modeling tool that's being used extensively in Pennsylvania, and that you're going to hear quite a bit more about in just a moment. So it was a really quick and easy way for the staff members of the NGO to say, oh yeah, this is the site. We're gonna work here. Okay. So whoops. So I did the web demo, and this is the time to ask me questions before I pass it on to Barry and to Bill.
Okay, thank you, Anthony, for that excellent presentation of this very exciting new tool. We're going to take a few questions now from the audience, and we have quite a few. One of the quick questions, Anthony, is what browsers are the Model My Watershed web app compatible with?
Excellent question. We have tried to make it compatible with all modern web browsers. It uses new HTML5 interactive animation technologies. So really old web browsers, and which include, I think, a lot of versions of Internet Explorer have bugs. However, Google Chrome, Safari, Firefox, and Microsoft Edge all should work. So we're testing all the browsers, and we're also have worked quite hard to have it work with touch screens, which are becoming more and more prevalent. The sizing, the web application automatically sizes. I'm just going to show you a little bit how that works. If I change the size of my screen, the web application should automatically resize. And so if you have an iPad or a tablet, you should be able to work it on a tablet. If you have a smartphone, especially a small one, things get a little bit too small. But tablets are definitely part of what we were aiming for in our testing. This also works on Chromebooks.
As a follow-up question, is there a preferred browser?
since a lot of our funding and a lot of our beta testers are school children, a lot of them have moved to Google Chrome, especially with Chromebooks being quite prevalent in schools, and also with Google applications for schools. A lot of students use Google Chrome. So that is what we get the most testing on. So I would say that would be maybe the preferred. But I use it frequently on Safari, and I know other colleagues use it on Firefox all the time.
Okay, great. We also had questions about, are there any plans to expand the tool to the U.S. territories and also to Canada?
Good question. We are very interested in expansion. At the last section of this conversation and webinar will be about what our immediate plans are based on funding that new funding that we just received from the William Penn Foundation, and also some of the ideas that we have for moving forward. In short, the Model My Watershed web application doesn't just represent the capabilities that are presently enabled, but rather it's kind of a sky's the limit. What we have demonstrated is the incredibly powerful combination of running high-performance geospatial applications on a cloud server in a web browser, and what really can be done with that. And we're have a very motivated and enthusiastic team to expand further. But we do need funding for an expansion, for example, to Canada. We've had conversations about all of these things. We've had conversations with lots of potential clients, but none of that. We don't yet have funding to work outside of the continental United States.
Okay, thank you. We also had a question about, can you make a circle instead of a polygon, like a 1 kilometer circle? Well,
so let me show you that. Let's see here. I guess I should just reset. The only way to do a circle would be to do a trace. So so you could do the free draw tool, and you could basically trace out a circle with as many points as you want. I mean, you can have a very detailed polygon. So there are different ways in which you could overlay something on your screen and trace around it. We presently don't have the ability to import a shapefile or a KML or a GeoJSON file that would allow you to design a boundary in some other application and then import it. But that capability is something that is presently under development right now, and we hope to release it this spring. So the ability to import a shapefile.
Okay, great. But you can get a facsimile of a circle.
Yeah.
Another question, a couple of people asked about metrics, and they wanted to know if you can use English metrics units instead of metric.
That is a feature that we have discussed doing, and I think that we'll probably be implementing it very soon. We just recently, as in less than a month ago, received new funding from the William Penn Foundation, and we'll be having a little design workshop with stakeholders and an end-user advisory committee in the next month, and I'm sure we're going to hear that request. So you can probably count on it within the next year or less.
Okay, well, I was excited to hear about the Monitor My Watershed app that you recently got funding for, and someone asked, are you looking to connect the water quality portal that USGS and the EPA run? It provides a great linkage to all STORET and NWIS water quality data, and would be a great source of water quality information, the questioner says.
That is an excellent question, and the answer is yes. So what I'm zooming to is the Delaware River Basin, because we have already implemented some early features of the Monitor My Watershed as test cases. So we already have NWIS stations streaming in using the various, this is USGS National Water Information System data that is streaming in with historical data in near real time, or the last couple months of data depending on the source. So that data is already in our system. We basically succeeded with that demonstration project. We're using Water1Flow web services and other open data sharing web services. That allowed us to also pull in data from the Delaware Environmental Observing System, which is a weather station network in these green points. So we have weather data, and our test application also pulled in NOAA tidal station data from NOAA. So we just used 3 different sources of data to kind of demonstrate our ability to pull all this data in. In addition to these little orange points are the NPDES codes, which we can just display without even doing an area of interest. So we are very interested in bringing in as much data as possible, data that has easy data services already, which already would enable us to fetch the data.
Okay, thank you, Anthony. We have many more questions, so we'll hope to get to some of them at the end. I would now like to introduce Dr. Barry Evans and Bill Brown, who are going to introduce the map shed and discuss some additional case studies. Barry, the floor is yours.
Okay, thank you, Ann. Hello, this is Barry Evans. I have a full-time research appointment at Penn State University, as well as an adjunct position at the Stroud Water Research Center. I'm going to be the primary presenter for the next 50 slides or so, but with me today also is Bill Brown, who is the chief of the TMDL section at the Pennsylvania Department of Environmental Protection. And Bill will be adding some commentary at certain points in the slideshow to expand on or clarify some points that we present during the slideshow. Anyways, going back to this slide here, I'm going to be talking now about what we call the multi-year watershed model that works within Model My Watershed. This particular model is based on a desktop application that my group developed at Penn State called MapShed. And to give folks on the line a better understanding of how this model works within Model My Watershed, I'm going to describe the history of MapShed and how it works in the desktop application. So first, a brief history. In terms of development, well, first of all, MapShed is a desktop application. This includes a GIS front end that's used to generate input data for the actual model, which is called the GWLFE watershed simulation model. This GWLFE is an adaptation of what's called the generalized watershed loading function model that some folks on the phone may be familiar with. The GWLF model was originally developed by Doug Hayes and Associates at Cornell University, and my group at Penn State has been using this and expanding it over the last 15 years or so. We've added enough new functionality to it that we now have started to call it the GWLFE for enhanced. Some of you may recognize this GWLFE model as being one of those models that is available within the EPA Basins model framework. The model I'm going to be talking about today is several years more advanced than the version we use in EPA Basins. Now, MapShed itself is an update of an earlier GIS-based package called AVGWLF, which again my group at Penn State developed. This was originally developed using an older version of ArcGIS or ArcView software that was available in the 90s called ArcView. And we used ArcView 3.x as the front-end geoprocessor and linked it with the GWLF model, which at that time hadn't been expanded so much. AVGWLF has been in use since about 1999 by Pennsylvania DEP and other researchers, including a group that I've worked with in Mexico. They have the Spanish language version of that. Over the years, we started to realize that ArcView was becoming less and less available for many folks, and we decided it would make more sense to use a non-commercial free GIS platform as the front end to our modeling tool. And we explored the use of MapWindow and decided on using MapWindow in about 2010. some of you may recognize Map Window as being the GIS engine that runs behind the current version of the EPA Basins modeling platform. So we started customizing Map Window to replace ADGWLF, and we released the first non-beta version in 2012. And it's been undergoing more or less constant revisions since then. Now, at this point, assuming Bill, if you're still on the phone, I'd like to have Bill provide some comments on, or give a little background on TMDLs and the modeling approach that's now being used in Pennsylvania. Bill, you there?
Yep, I'm here, Barry. Can you hear me?
Yep.
Good. All right. Well, Pennsylvania was one of the states in the late 1990s where lawsuits were brought against EPA for not enforcing sections of the Clean Water Act, and TMDL development was driven by consent decrees for a while. So in conjunction with Barry and his group when he was still at Penn State, we used ADGWLF and Watershed for every non-point source TMDL that we did over approximately a 10 to 12 year period. Then as we moved out of litigation-driven TMDLs, there was an increased interest in urban stormwater, especially with EPA's characterization of municipal storm sewer systems as point sources requiring waste load allocations in TMDLs. That timing kind of coincided with the development of Pennsylvania's new NPDES permit for small MS4s and our need to provide a kind of a planning level tool to permittees and stakeholders to meet certain requirements that we wanted to have in that new permit. I think we're going to talk a little bit more about some of those requirements later. So we've been working with Barry over the last 5 years or so as he's made Watershed a much stronger tool in a lot of areas like urban hydrology and stormwater BMP modeling and other kind of model output post-processing techniques. So that's about where we are right now.
Okay, thanks, Bill. At this point, I'd like to talk about some of the core components or functions of Watershed, again, the desktop modeling package. Again, Watershed includes a GIS engine up front, which is used to overlay and manipulate, process different GIS data sets and weather files for the purpose of creating an input file for the core watershed simulation model, which again is GWLFE. So once that input file has been created, the GWLFE model can be run to estimate nutrient, sediment, and pathogen loads for any given watershed or collection of watersheds in a given area. And by nutrients, I'm specifically talking about nitrogen and phosphorus. Within the GWLFE model, we have included another module, which is essentially a BMP simulator, which allows users to evaluate the potential benefits of implementing different types of BMPs across the watershed. BMPs that might be implemented in both agricultural areas or urban areas and so forth. And lastly, and I won't go into too much detail here, but there are other tools associated with Watershed that can be used to visualize and evaluate and compare different types of model output. So the way the desktop version works is that once the software has been installed on the user's computer, the user clicks on an icon and opens up the Watershed Project Manager. And one can either open up an existing project or create a new one. Assuming that one is creating a new one, one has to load different data layers. Now in Pennsylvania, we've gotten funding through Pennsylvania DEP to actually prepare data sets for the entire state that can be used to drive the model. We've gotten other additional funding for other places, particularly in New York and New England, where we've gotten some funding from EPA to develop some regional data sets up there. In areas outside of this region, we have included instructions in our Watershed user manual on how users can construct their own data to feed into the Watershed model. So again, in preparing a model, one first loads different types of data layers, and this includes information on streams, watershed boundaries, soils, land use, topography, and so forth. After these data sets are loaded, the screen looks something like what you see here. The user then selects one or more subbasins to prepare an input file for. In this case, the entire watershed has been selected to create one input file for the larger watershed. The user then specifies a couple other bits of information like simulation period and growing season. And when they're ready, they click on this OK button right here to basically start the processing. So Mapshed starts manipulating and processes this data and then creates an input file, which we call a GMS file, to load into the actual model, the GWLFE model. So once the model is open, you can load an input file, you can review it, and this is some of the input that's been created by Mapshed. For example, in the lower left, this shows some of the nutrient-related data that's been populated automatically by using the input data. To the right is information related to animal farm animals in this particular region. The user, if they wish to, can edit this information as well. For example, somebody might want to provide some better information as to point source discharges or maybe better estimates of different farm animal populations. This type of information can be edited and saved. So when the user is ready to run the model, they actually just hit go, or back up one step, they provide an output file and then hit the run button, and this literally takes only a couple seconds. And after running the model, different types of output are provided. And there's quite a bit of information, and I don't have time to show all of it, but basically hydrology and load information are provided on an annual, monthly, and daily basis, and different forms can be used to explore this kind of information or the model results. We also write all of the output to Excel files so that the user, if they wish, can graph and plot this kind of information in Excel using the tools available in that software. Now, another important module that we've added over the original GWLF model is the ability to simulate different BMP scenarios. So what the user can do here is hit the Edit BMP Data button, and then the user has the ability to basically specify different levels of BMP implementation for both rural land and urban land within a given watershed. So, for example, the user can simulate conservation tillage, nutrient management, animal waste management systems, vegetated buffers, stream bank stabilization, and a host of other BMPs in an agricultural setting, and there are a number of specially designed urban BMPs that can be simulated as well. Now, this urban BMP scenario editor shows kind of the last version of the model. We've actually updated this, and I'll show you what that looks like a little bit later. But actually, once you've added some BMP data, you can then compare in kind of before and after mode the results. So, for example, on the screen here, if I look right at the end of this column right here, this is load information for phosphorus before BMPs were applied, and this is the information after BMPs are applied. So the user can, in kind of iterative fashion, keep specifying different levels of BMP for the purpose of comparing load results to see what kind of reductions can be achieved in a given watershed. Now, the software itself, Mapshed, is available at our website called mapshed.psu.edu. And one can also download the user guide to see, how the model works and what type of data layers are used there. So that is a very quick overview of the Mapshed tool itself. What I'm going to talk about now is how some of these components have been incorporated into the Model My Watershed framework. So some of the key activities here included, first, we had to reproduce the geoprocessing routines in Mapshed so that they work equally well in Model My Watershed. In Mapshed, we use the map window default functions to overlay and analyze different GIS data sets. In Model My Watershed, these geoprocessing routines are handled by functions such as GeoTrellis, GDAL, and PostGIS. I don't want to go into too much detail here, but if anybody's interested in how this is done, actually Anthony's going to be talking about a repository for some of this code later on, so I'll just leave it at that. So we had to basically duplicate the geoprocessing routines that currently exist in Mapshed to Model My Watershed. Then we had to reprogram the actual GWLE model. Now for Mapshed, this model is written with Visual Basic. This was for Model My Watershed. This was completely rewritten to Python to allow for multi-user processing on Linux and an Apache Spark engine. And I won't give too much description here of what that means, but Anthony's going to go in a little bit more detail about this later on. Now this is an important feature here, recoding this in Python, and particularly the way it works in Model My Watershed. In MapShop with the desktop application, of course, you can only have one user hit this at a time, but with Model My Watersheds, you can have many users hitting multiple watersheds across the U.S. You can have many users hitting the same watershed, and this really won't affect the processing, which is really a pretty big leap forward in terms of modeling on a web application. Next, as I described earlier, for Pennsylvania, New York, New England, a couple other areas, we have some pre-prepared maps data sets that somebody could use, or a user can construct their own. However, this can be kind of tedious for areas outside where we don't have data. But with the Model My Watershed, what we've done is we've basically substituted these smaller data sets for national data sets. So we've got many national GIS data sets that are used to drive this model. And I will be talking about some of them in just a minute. Lastly, to make sure that the processing and modeling was being done equally well, or at least we were simulating what could be done on the desktop, we were constantly comparing Mapshed output with the output we got on the Model My Watershed, kind of as a test. Now, I'm going to talk about some additional data sets that have been built into Model My Watershed. Anthony described some of these. He talked about the USGS National NLCD, National Land Cover Database that we use. We also use the USDA gridded Surgo data, GSurgo data. In addition, we use weather station data for the entire U.S. This is kind of a limited data set at the moment. We hope that we do plan to expand this, but for now, we have taken weather data that we got from the US EPA website. You can download 30-year data sets that have been compiled by EPA for the purpose of driving other EPA models, and so we built this into Model My Watershed. So we essentially have 30 years of daily weather data for about 300 weather stations across the U.S. We also have a national groundwater nitrogen layer. This was developed by USGS with some modeling that they did. Basically, this map represents different concentration of dissolved nitrogen in shallow groundwater, and this is used to help with the subsurface model in GWLFE to transport subsurface nitrogen to nearby streams. We are now in the process of incorporating a soil phosphorus map that was recently prepared by USGS at a national scale. I say soon here because when I prepared this, we had planned to do this, but with the additional funding we just got that Anthony mentioned, we are now in the process of building this into Model My Watershed. So this is an estimate of soil phosphorus in the soil, developed with sample data by USGS, and they developed this national map that we're going to use to set certain model parameters. We are also going to be using a national base flow map developed by USGS. Base flow, as some of you may know, is that, well, stream flow is primarily composed of a base flow and a direct runoff element, and this base flow essentially tells you how much slow release groundwater flow is going into a stream versus direct runoff, and we're going to be using this map to regionally set what's called the groundwater recession coefficient in our GWLFE model. We also are going to be using a soil nitrogen map that was recently developed by Oak Ridge National Labs. In Pennsylvania, in the northeast part of the country, we essentially use a default value for soil nitrogen, but we realized that soil nitrogen concentration varies considerably across the U.S., and we hope to use this map to reflect those differences. Now, I mentioned earlier that we are currently using about 300 weather stations with about 30 years of daily weather data. We know, however, that the National Weather Service has daily weather data for about 10,000 weather stations across the U.S. And we soon hope to start compiling some of this information or coming up with a process for extracting this information instead of using that previously compiled 30-year data set. This will not only give us better estimates of precip and stream flow across the U.S. in specific locations, but it'll also be more current. And this will help for some calibration efforts that some people may be interested in engaging in using this particular model. Lastly, we plan on incorporating something called the cropland layer, which some of you may be familiar with. That's been produced by U.S. Department of Ag. Anthony mentioned, and I mentioned, the USGS National Land Cover data set, the NLCD data set, which is 2011 vintage, that we currently use to drive the model. Some of you familiar with this know that with the NLCD data, we have representations of different land use cover categories across the U.S., but for example, in agricultural areas, we really only know whether it's cropland or hay pasture. What USDA has attempted to do with this particular layer is actually represent the crop type that may be growing in any particular location across the U.S. So instead of having a pixel value, if you will, or an area that represents cropland or hay pasture, with this data set, you can actually get an estimate of how much corn, wheat, sorghum, soybean, etc. is being grown at any particular location. And this will better enable us to set certain model parameters and estimating certain things like nitrogen, phosphorus transport. Okay, at this point, Bill, I believe Bill has a few more comments about data sets and storage and issues we faced in Pennsylvania. You ready, Bill?
Sure. Yeah, not a lot to add here, Barry, but more just a general comment on the conversion from the desktop map shed to the model my watershed. Back in the early years, it really was a balancing act where the computer issues of users, like storage space, speed, along with logistics of distributing the model, dictated the use of more generalized data sets like StatsGo for the soils, and sometimes even splitting data sets by region to make them smaller for distribution. But then the move from ArcView to the free GIS software package Map Window, so users didn't have to buy an expensive commercial GIS software, was well intended, but changes in the Windows operating systems over the years and security updates that were constantly being patched in created real instabilities in the free GIS software that were really hard to overcome. So this move to the web-based system and the model my watershed with cloud storage and computing is really huge, as it not only solves the problems related to platform and speed, but it's also going to make for a much better model in terms of watershed characterization and load estimation with the new data sets added that Barry and Anthony have talked about.
Okay, thanks, Bill. Next, I'd like to move on to demonstrating how Model My Watershed, both the current version and the future version, could be used to support different types of activities. And I've got 3 case studies I'm going to show. In this first case study, I'm going to show how Model My Watershed could be used to support the development of a watershed improvement plan based on a prior TMDL assessment. Now, at this point, I'm going to ask Bill to jump in again to discuss a little bit about the TMDL and modeling process in Pennsylvania.
Okay. Like most states, Pennsylvania doesn't have any numeric criteria for sediment and nutrients. So all the TMDLs developed for those pollutants were done and are still done using a reference watershed or paired watershed approach, where we match the watershed characteristics like land use and geology, hydrologic soil group, size, in a watershed that's meeting water quality standards as closely as possible to the impaired watershed. Then both watersheds are modeled, and the loading rate in the attaining watershed is assumed to be the allowable loading rate for the impaired watershed, and used to set the allowable load. but it's the relative difference between the impaired watershed and the attaining watershed that counts in the TMDLs, not the actual difference in the load. So that means we just need to maintain the percent reduction from the original TMDL in any subsequent efforts, to kind of what Barry will talk about, to implement the TMDL that include any sort of remodeling.
Okay, thanks, Bill. So what I'm going to do here is talk about, again, how Model My Watershed could be used to support the development of a watershed improvement plan. And in this case, the basic steps that one would take would be first to run the model to estimate the pollutant loads from various sources for the purpose of evaluating where the focus should be placed with respect to future BMP implementation and remediation efforts. So here again, we would use the Model My Watershed to model the current loads. Once these loads have been identified and quantified, we can then use Model My Watershed in kind of BMP scenario mode to simulate what load reductions might be possible using various BMPs and remediation measures in order to assess, whether a certain target reduction can be achieved. For my example, I'm going to be using a watershed called Conestoga Creek, which is in central Pennsylvania. This is just a map of the watershed showing some of the streams where they have been identified as being impaired or not impaired. Basically, you can see the reds are the impaired, or they were not attaining their water quality standard. So in this case, a stream assessment was done, determined streams were impaired, a TMDL analysis was done later, and it was determined that based on an analysis in comparison with a reference watershed approach, or reference watershed, that the total phosphorus should be reduced by about, I should say it was recommended that the total phosphorus should be reduced by 38%, and that the sediment load should be reduced by 44%. And various groups within DEP and outside of DEP are now looking at possible implementation plans to see what might be most effective in achieving these reduction targets. Now, in the past, AVGWF and then MapShed has been used in Pennsylvania to kind of simulate pollutant loads and these potential reductions based on BMP implementation. But Model My Watershed has now progressed to the point where it can now be used to accomplish the same type of analysis. So at this point, I'm going to go to Model My Watershed, just like Anthony did earlier. And what I've got showing here is an area near Lancaster, Pennsylvania. I'm going to draw the, I'm going to get, hang on one second. There we go. I lost my little tool here to draw the watershed. So I'm going to draw some watershed boundaries here. In this case, I'm going to draw some HUC 12 boundaries. And I'm going to show you where that particular watershed here is the Conestoga. This is the Conestoga right here. What I'm going to do is first model the load. I'm going to use another feature here. Anthony used the free draw option. I'm going to basically say I want to model my load at the HUC 12 level because in this case the Conestoga Creek watershed is a HUC 12. So I'm going to click on this, and immediately, as was done with the earlier site model demonstration that Anthony showed you, different data sets are being clipped out and summarized. So at this point, I can look at the land distribution, I can look at the soil distribution, I can look at an estimate of farm animal populations. Now, Anthony alluded to this earlier. I didn't really show a map of this, but within Model My Watershed, we've incorporated a national map that shows, that gives county-level population information for all sorts of farm animals. And based on that, we've estimated the populations for things like chickens and dairy, beef cows, and so forth within this particular watershed. We've also got, I believe, a point source here, which is located right there. So at this point, I get a summary of the data, but what I'm interested now, or want to show you at this point, is how one would use this other model that we call the multi-year watershed model, which is basically MapShed that's been web enabled. So if I click on that, immediately what happens is that some further information is being extracted from different data sets under the hood, as Anthony would say, and different combinations and analyses are being done to calculate things like curve numbers for different land use categories and factors related to USLE equations for calculating soil erosion and so forth. But anyways, once that data, now what is different here with the MapShed desktop version is that with MapShed, the desktop version, you can see the input file here, but with the way we've enabled or incorporated this version in Model My Watershed, the model is run immediately. So the model has already been run, and we can look at this point, we can look at different types of hydrology output. For example, we can surface flow, surface runoff, and so forth. And we can get a breakdown by month of what the typical precipitation, ET, surface runoff, and so forth is for this particular watershed. We can also look at the water quality output. In this case, the model has estimated, using 30 years of weather data, the mean annual loads for these different source areas, as well as due to stream bank erosion coming from point sources, subsurface flow, and so forth. Now, what I'm going to use here for this first example is the total loads. What we're primarily interested in when we're doing TMDLs in Pennsylvania is calculating mean annual load. In this case, I've got a mean annual load for this watershed for sediment, nitrogen, and phosphorus. Now, at this point, I'm going to kind of go to a split screen mode because I want to show you that what we want to do here, having run the model, as I indicated in a prior slide, it was determined that the targets we were shooting for phosphorus, let me get that out of the way here. Oops, there we go. For total phosphorus, it was recommended that we reduce that by 38% and sediment by 44%. If I take these values right here, these have been transferred to the slide right here. So based on the modeling, we've calculated the mean annual total phosphorus and sediment loads were estimated to be 18,316 kilograms per year in the case of phosphorus and 7.6 million kilograms per year in the case of sediment. Now, if we use these target reductions above, we can then calculate how much do we need to reduce these loads by to get a target load. So we can take those initial loads and reduce them, in this case, by 38%, so that our new target load is 11,356 kilograms for phosphorus and 4.2 million kilograms per year for sediment. Now, given that these are our target loads, what we can now do is kind of move into BMP scenario mode with Model My Watershed, and I can do this under a new scenario. So what I can do at this point is to say, well, let me go back over here to my screen. I can see by the output that some of the loads are coming primarily from cropland and farm animal operations. So maybe that's what I should focus any BMP implementation on. So, for example, I can implement nutrient management within that watershed. And what this is telling me is within the Conestoga Creek watershed, we've got about 2,700 hectares of row crops. And maybe we can see what would happen if we applied nutrient management to about 2,500 acres. We can say apply. Immediately the model is rerun, and it will give us a new load information down here as soon as it's complete, which it just did. So if I bring my slide back up, I can see that this original phosphorus load was 18,316. I've reduced it now to about 16,484. And similarly, well, I haven't done much with, actually anything with sediment, because if you remember, what I applied was just nutrient management. So I haven't affected the sediment load yet. So what I can do is include some additional BMPs. For example, maybe I want to do, let's say, vegetative buffer strips. Oops, wrong one. That's in an urban area. Let me back up again. I want to do that within the rural landscape where all the ag land is. So what the model has told me is that I've got about 22, 23 kilometers of streams running through agricultural areas, and maybe I might attempt to try to put buffers on, maybe 80% of that. So I can specify 18 kilometers where stream buffers would be applied, rerun the model, and I can see right here I've taken that 16,000 kilograms per year load down to 13. And I can continue this with maybe adding livestock waste management. And what it's asking me is, okay, what percent of the animal population are you applying this to? Now, AEU refers to animal equivalent unit, and all that means is the 1,000-pound weight of a given animal. So if I say 50, I'm basically applying it to 50% of the animal load, if you will, in terms of mass. And I can then see what happens if I apply some animal waste management systems. And now that hasn't done much here, but it actually has done, well, actually it's reduced that a little bit, but not a whole lot. The buffer has got me, the vegetation buffer has got me a little under 6,000. Anyways, the point here, and I wanted to bring home, is that I've got a current load and a target load here, and what I can do is calculate the current load with Model My Watershed and then iteratively go through different BMP scenarios to see what kind of reductions I can achieve to get me close to that target load. Now, the other thing that we can do with this particular version of the model is I can actually download the input file that was created for the model itself, something we call, again, a TMS file. This is actually downloaded. In this case, I downloaded it to my download folder on my laptop. What I can do is open up the desktop version of the model and then load this particular, it's the download site. This is the GMS file, the model input file I just created. You can see it says 2/28 and today's date. I can load this. I can actually look at the data that was created, and I can also modify this if I choose to. For example, I can maybe modify the point source data, or I can modify the animal data here, change the animal numbers. What this allows me to do if I download the model is there are a few more options available on the desktop that aren't yet available on the web version, but these are things we hope to implement soon. Anyways, that's that particular case study. So let me move on to the next one. So in terms of the next case study, what I want to do is show how Model My Watershed has some current features can be used to assist in a simple MS4 application. In this case, in Pennsylvania, some new guidance has been put out by the Pennsylvania DEP, the state, that requires regulated areas, for example, MS4s, to develop a pollutant reduction plan to reduce sediment loads associated with their jurisdictions by at least 10%. And this is going to be part of the NPDES permit process. So entities have to show that they have to model their area and show that they have a way to reduce their sediment load by 10%. And in this particular example, I'm going to show a simple way how one of the features in Model My Watershed can be used to assist this in kind of spreadsheet fashion. Now at this point, I believe I was going to ask Bill if he could add a few more comments on this PRP approach as it's being used in Pennsylvania.
Sure. Like you said, Barry, as part of Pennsylvania, the permit the new permit for small MS4s that I mentioned before, permittees that have outfalls discharging municipal stormwater either directly to or within a certain distance upstream of sediment-impaired waters have to develop this PRP, or a pollutant reduction plan, and they have to demonstrate a 10% sediment reduction through BMP implementation in this permit term. So we have a pretty diverse group of municipal permittees with different levels of both human resources and fiscal resources. So what we wanted to be able to do was provide a range of tools, including Mapshed or Model My Watershed, the multi-year, in a range of tools and methods that would allow anyone access and to be able to develop this sort of plan that's going to be required by the permit. And just a couple quick additional notes on that. Pennsylvania is a little bit different in that the townships and the boroughs are permittees in Pennsylvania, and not the counties. So there are going to be over 1,000 separate entities trying to develop these load reduction strategies. And as a way of keeping things fair amongst all of them, we've kind of limited the methods accepted for determining the BMP reduction efficiencies. And one of the allowable methods is to follow the calculations in a set of expert panel reports used in Chesapeake Bay reporting and modeling. And that methodology is currently in the desktop version of Mapshed. And my understanding is that Barry's going to talk about it, but it's also going to be incorporated into the Model My Watershed multi-year model over the next few months.
Yes. Okay. Thank you, Bill. So now, to do the simple approach, the basic steps are as follows. First, we are going to use Model My Watershed to quantify the distribution of land use cover within a given MS4 or regulated area, which is usually a municipality or urban area in Pennsylvania. We would enter this distribution land use cover into basically a spreadsheet, and then we would apply the acres of area, the different land use categories. We would multiply that by loading rates that have been established as part of the Chesapeake Bay model. Most of Pennsylvania drains to the Chesapeake Bay, and as part of this PRP guidance that's been put out to the state, users can basically calculate loads using these established loading rates that are based on the Chesapeake Bay model. Now, once the loads have been established for a current area, a municipality, for example, would also have to come up with a plan to remediate those loads using different types of BMPs. And the reduction coefficients that they would use are kind of set forth or explained pretty explicitly in DEP's guidance. And much of the BMP load reduction coefficients are based on what's called the performance standard approach, which again is part of this expert panel report that the Chesapeake Bay program developed for use in the Chesapeake Bay model. So what I'm going to do at this point, I'm going to again minimize my slideshow. I'm going to go back to another area in Pennsylvania. I'm going to reset the model, and I'm going to the arrow for my enlarging and zooming in and out isn't visible on my screen because of the chat box here, but that's okay. Let me go back out to the state. So what I'm going to do here is go zoom in an area around Pittsburgh. Oops, I got to move that. That's funny, I can't see that enlargement tool here, but I'm going to go to an area just north of Pittsburgh.
There's a way to minimize that chat box. There's a little orange arrow.
I've already got it over. Actually, I can move it completely out of the way, I think. There we go. There we go. There we go. Thanks, Anthony. Okay, let me zoom in. Again, I'm going to be looking at an area just north of Pittsburgh. It's this area right here that I've got my hand over. And what I'm going to assume here is that there's a municipality located within this particular watershed, and they're being requested to reduce their contribution to this watershed, at least the sediment load, by 10%. So using a simplified approach, what we can do is, if we know the municipality boundaries, and I'm just going to wing it here, I'm going to assume this is the municipality boundary. I can draw a boundary right here. I'm going to, and in fact, this particular municipality does cover most of this watershed. But I'm going to assume this is the municipal boundary here. And what I'm going to do is basically calculate the distribution of land use categories within this area and use this distribution of developed areas and non-developed areas in kind of a spreadsheet approach to calculate my reduction. So basically, I'm going to take information provided here on square kilometers of developed land. There's 4 categories: developed land here. Everything else is going to be thrown into a non-developed land category. So if I go back to my slide set here, what I've done, and I'm going to expand this in just a minute, but I just want to show you I've taken the distributed land use data here, recalculated to acres, so that for this particular municipality, I've calculated that I've got so many acres of developed land, everything else is getting thrown into an undeveloped land category for a total acreage count of 5,456 acres. Down below, I've got some loading rates that have been established by the state that people can use that are based on the Chesapeake Bay model. And what they've done is they've come up with loading rates for both impervious land and both impervious and pervious fractions of developed land, and then a loading rate for everything else which is being thrown into an undeveloped land category. So what this means, I'm going to open this up here. So once I've transferred this load information to a spreadsheet, and this is a representation of a spreadsheet, I can basically take this acreage information, multiply it by these loading rates, to calculate total nitrogen, phosphorus, and sediment loads. So for example, for undeveloped land, I can take 2,198 acres, and then I can multiply it by these loading rates for nitrogen, phosphorus, and sediment, and derive these total loads for undeveloped land. Now for developed land, it gets a little bit more complicated, but it's still pretty straightforward. What I want to do here is take the impervious fraction of this and calculate a load, and then both the impervious and the impervious fraction and calculate a total load. So what I would do if I want to calculate the impervious fraction, by the way, these are just estimates of impervious fraction that come from the NLCD data set, but I can, for example, take 951 acres, multiply it by 0.15, and then multiply it by the impervious loading rates for nitrogen, phosphorus, and sediment to get the impervious load, and then I can do the reverse and take what's remaining, in this case 85%, or 0.85, multiply it by the 951, and then multiply that by the pervious loading rates, and then add up the two to get a total nitrogen, total phosphorus, and total sediment load for all of those categories. And if they are then summed, these totals represent what would be the total nitrogen, phosphorus, sediment load calculated using existing acres and these loading rates. Now, having this, then using a simplified approach, I would then have to calculate what would be a typical reduction coefficient that I might get with a particular BMP type that I might want to apply in this area. Now, going back to my curve, these curves have been set up for to be used by the state. So the way this is used, I can say, well, I'm going to employ a particular type of urban BMP, and for the purposes of the PRP preparation, all BMPs have been thrown into two categories, either runoff reduction, RR, or stormwater treatment. So I can, if I'm planning to use, in the RR, as you can see, give you a higher coefficient. So basically, the way this works, you would, in designing an approach, you would say, my plan is to capture so much runoff per impervious acre, so many inches of runoff with a particular type of BMP, and then I can look at this axis and see what kind of reduction I should apply. And as you can see, it's kind of a dynamic calculation because the amount of reduction coefficient removal you would get, in this case with sediment, is totally dependent on how much runoff you capture. And that's the way this performance standard option works in the new Bay model and the way we've implemented it in the desktop version of MapShed. In our case, we would pick a particular coefficient and then apply it against those loading rates that we've already set up in the spreadsheet. So for example, if we've got these existing loading rates, we can then say, well, what happens if we capture 1 inch of runoff and we apply it to all of the developed land within this watershed? Well, what we would then do is use these coefficients that we pulled off of the curve. Now, I only showed you the coefficient for sediment, but similar curves can be used to calculate reduction coefficients for nitrogen and phosphorus as well. And that's what that's what's represented right here. So in this case, I would take the loads. Now, in this case, I'm assuming that the undeveloped land is not treated. No runoff is captured, so those loads are left untouched. But in this case, we're assuming that we're going to apply some BMP or set of BMPs across all of the developed land and apply these reduction coefficients. So in this case, for developed open for nitrogen, phosphorus, and sediment, if we apply these reduction coefficients, we get these reduced loads of nitrogen, phosphorus, and sediment as shown. And if we sum all of these loads up, we can see that we've got a reduced load here versus the starting load, reduced phosphorus versus starting nitrogen, and sediment versus the starting sediment. And then we can calculate, well, with this simple approach, what are we getting in terms of a load reduction? Now, in this case, the target load for sediment for these PRPs is 10%. But if we assume we're going to capture 1 inch of rainfall across all of the developed land, we actually could get a reduction of about 60%. Now, what this tells us here is that we're shooting too high. So what we can do is go back and either reduce the amount of area that we're treating with this BMP, or we can reduce the amount of runoff that's captured. So in another fashion, we can then calculate these load reductions. So anyways, that's the simple approach. Now let me quickly go through what we plan on doing on a more comprehensive approach, and I'm going to have to use by example the way we do it in MapShed. And I'm looking at the time here, and I see I need to go a little bit quickly, so I'm going to run through this in about 5 minutes. But basically with MapShed, we have the ability to estimate pollutant loads for a watershed and then redistribute those loads among one or more urban areas or municipalities within that watershed. So in this case, we use MapShed to estimate a particular load reduction within one or more urban areas. Once we get the current load, we can estimate the load reduction that we might achieve by applying different BMPs within that watershed. Now in this case, what's needed, which we don't have yet working or existing within Model My Watershed, is something called the Urban Area Tool. So basically, to use an example here, I've got a watershed outside of Philadelphia called Skippack. This is the land use within that, and in this case, all of the oranges and reds and pinks represent developed land, and the greens and browns represent non-developed land, which are primarily forest and ag land. In this case, the watershed is about 40% developed. Now, with MapShed, we can actually introduce an urban area layer, and this is what it would look like. This area shows municipalities or urban areas within a municipality. For example, this is the urban area that exists within Skippack Township. And what we can do is introduce this as another processing layer in MapShed. So the way this works in MapShed is we load the different layer, and this time we include an urban area layer. And so when we run MapShed, what actually happens is that the load is calculated not only for the entire watershed, but loads are calculated for each of these urban areas as well. So when we run the input file in GWLFP model, once we've introduced this urban area layer, we can look at the loads in another tool we call the Urban Area Viewer. And with this viewer, we can look at the total loads for the watershed, as shown here on this bottom row. And we can also look at a municipality load tab. In this case, I've got the loads for Skippack Township. and I can see these lesser loads that are being attributed to Skippack Township, including not only these upland loads, but more importantly, the stream bank contribution as well. And that's because we've incorporated the stream bank routine within Mapshed. So, and after doing that, we can also run different BMP scenarios to see what we might be able to do in terms of reducing those loads within each of those urban settings, urban areas. Okay, let's see, I think I might have time for, this isn't so much of a demo as much as it is to just show you that the way this is working right now. I'm going to do a quick reset. I'm going to zoom out, go to an area north of Philadelphia. In fact, this same Skippack watershed, which is this one right here. Now, with the current version of Model My Watershed, I can calculate the load for this, but as I said, what I can't do is calculate the load for an urbanized layer, which we have kind of built into Model My Watershed, but at this point it's only visual. So what we're now doing is we are going to build in the routines to calculate loads not only for the watershed, but for each of these urban areas as well. And once we've done that, we'll be able to do all of the PRP support work, if you will, within Model My Watershed. And okay, so I think at this point I'm done. Bill, I believe you had one or two more comments you wanted to add here?
Maybe, Barry, just to say how, that this is an example that really highlights all the major enhancements Barry has made probably over the last decade to the original model. Back in the day, so municipal stormwater impacts or a downstream channel or bank erosion issues. So back in the early 2000s, Barry incorporated, like you mentioned, an empirical channel erosion routine into the model that gives explicit loads for the sediment created there, and it's been peer-reviewed and published. And then that urban area tool breaks out both the overland flow loading and kind of reverses that stream bank erosion routine, redistributes the stream bank erosion load that's calculated at the outlet back to all the contributing municipalities. So those loads by default, like Barry mentioned, are for the urbanized area right now, but we're hoping to incorporate the option in the future to allow users to import manually delineated storm sewer sheds. And then just finally, with the new urban DMP routines and the urban area tool incorporated and the increased speed and stability and accessibility in the conversion to the web-based Model by Watershed, this is really exciting stuff for Pennsylvania, for DET. So we're grateful and appreciative of all the work that Anthony and Barry put in, along with all the partners that Anthony mentioned earlier that invested a lot of resources to make all this happen. So I'm looking forward to seeing other applications of the model now that it's going to be available nationally on this platform. Thanks, you guys.
Okay, thanks, Bill. At this point, I can see by the clock we're running a little slow or late. I'm going to ask Ann, should we hold questions till the end? Because Anthony has a few more slides he wanted to present.
Okay, well, that is maybe a good strategy. Thank you very much, Barry and Bill, for your excellent presentation. And given that the clock, we're getting a little short here, maybe we'll just dispense with the questions and we will move to Anthony giving some presentation about some of the future directions. As we move the slide, just for one moment, I want to ask one question of you, Barry, to give us just a snapshot summary of the primary differences between Mapshed and Model My Watershed. I understand these are two different things, but you're moving toward Model My Watershed. Mapshed is the old application, but maybe that would help our audience.
Sure. The primary difference is, of course, Mapshed is a desktop application, so you can only run it on a desktop. The model itself has been incorporated into Model My Watershed, and the model is exactly the same. Some of the data sets are actually different because, for example, in Pennsylvania, we've got some detailed data sets in Pennsylvania that we're not using for the national level, and we've got national scale data sets in Model My Watershed that we really aren't using for the desktop version. So we've got slight differences in input data, and the weather data is somewhat different because for Model My Watershed, we've got 30 years of data, and for Mapshed, we've got about 20 years of data, and the period of record is a little bit different. For Model My Watershed, we're actually using data from about 1960 to 1990. It's 30 years of data, good enough to drive a model, but not good enough for calibration work. And we hope to rectify that in the near future.
And I'm going to take the liberty to ask one more question, because there are a lot of people that are very excited, it seems, to use this tool. And one of the questions they ask, how do you download or actually save the analysis of the output for a particular area of interest? So those that want to jump into this right now, how can they save their work?
Right now, we don't have the ability to download the results per se, but that's something we are currently building in as a feature in this modeling application. So we're looking at capabilities to generate a report. As I said, right now, if you really want to get the results, you could download the input file and run the model on your laptop, and then you had all the results right there. But currently, we're only showing the results on the screen, but we're soon going to be developing some reporting tools to download the results and also some output as well, like export some shape files and so forth, but that's coming soon.
I'll add to that to say that
Anthony, maybe that's a good segue to some of the future directions. So Anthony, take it away, please.
That's perfect. I'll try to go quickly. I'll just add to that cutting and pasting those tables that are in the side panel into Excel works really well. We made sure that that was a capability. Sometimes cutting and pasting from a website into Excel doesn't work well, but we ensure that it does. So I'm just going to quickly mention that the Model My Watershed web application is still under active development. You've heard that. We've built this on a scalable cloud infrastructure for high performance and massive data storage. We're already doing some impressive things, but the scalability is designed to be almost infinite. We're also developing it on a 100% open source software stack, so there are no software licensing fees, and so that we have full control over the features that we develop. For those of you who want to ask more about that, you can email me later. One of the other things that we've done to kind of create this big data water application for everyone is that we've partnered academic modelers from multiple institutions to prototype cutting-edge code and professional code, provide support for bug fixes, and we've partnered with a professional software engineering firm that has really exceptional experience at designing user interfaces, developing user experience, and these kind of partnerships between water professionals and software engineering professionals I think is really key to make an application like this zing. It's really been fantastic. I'll just mention I mentioned that William Penn Foundation has funded phase 2. We're going to be developing a lot of enhancements right now, including import-export, like Barry mentioned, better share and compare features, improving performance. We're adding those Monitor My Watershed capabilities and bringing training materials, both in the form of workshops, but also much better online documentation. So stay tuned for that. But what's really exciting is where we can go with this. We are very open and interested in further development. That's basically our business model for maintaining this as free. We currently have the resources to keep the lights on, so to speak, for the next 2 years, and we're going to add a lot of features in those 2 years. But for Model My Watershed and the Wiki Watershed web app to be sustainable, we need new projects, new sources of funding, and we have the vision to add new models like the ones you see here, add new modeling features such as detailed site design, enhanced data, either future forecasted data, localized data, global data, and add model output viewers and explorers. A lot of states have developed calibrated model results for TMDL work, and we could just be a visualization platform for that, or maybe we could even add automatic calibration capabilities. Maybe we can have a viewer for the National Water Model. I'm going to show a super fast demo here where we've already done that. Basically for the William Penn Foundation, we've added extra features. I'll zoom in here and show you. If you can see on the right, I'm looking at the Delaware River High Resolution Stream Network. So in this little watershed north of Bethlehem, that we can see first-order streams. This is the NHD plus stream network. This is the high-resolution stream network that shows every first-order stream. If we want to do something like modeling areas in here, whoops, I shouldn't have done it quite like that. I'm going to reset. If we want to model some Huck 8 basin in here, but let's say there are a couple Huck 8s that are not Huck 8s, I'm sorry, Huck 12s that we want to model, that we want to aggregate at this USGS gauging site. There's another feature that we have, which is we have the ability to delineate a watershed at any given point, even if it's not on a Huck boundary or any other boundary. Rapid watershed delineation works for the entire Mississippi Basin. But what's really interesting here is this ability, the model output from MapShed has been aggregated to the Huck catchment level, not the Huck catchment level, the NHD plus catchment level, and we have the ability to actually view the loading rates for nitrogen, phosphorus, and sediment for these little areas within there, and how they get routed down a stream network. So you can see how, for nitrogen, which of these sub-watersheds are where the problems are. This is really an enhancer viewer for calibrated, highly developed model output. We could do this anywhere in the country or even anywhere in the world. So that's the kind of direction that we want to take Model My Watershed. So with that, thank you all for joining us, and I'll hand things over to the organizers.
Okay, thank you, Anthony. We're now going to have time for a few questions, but first I have a few announcements. First of all, we want to let you know that if you didn't have your question answered today, you can contact the speakers at this contact information. We also have a copy of the PDF on the website if you're not able to record this very quickly. And I want to let you know that we're currently planning our next webcast, which will be on March 23rd, and the topic will be the condition of the U.S. lakes and streams, findings from the National Aquatic Resource Surveys, or affectionately called NARS. We hope that you will join us for this webcast. The website will be updated soon with registration for this, so please check back with us at www.epa.gov/Watershed Academy for more details. And also, please don't forget to download your certificate if you like. The certificate can be downloaded from EPA server through the link that is provided on this page. So please type this link into your browser to download a PDF document, and you can personalize the certificate with the names of everyone watching from your location. And finally, when this webcast is over, an evaluation survey will be shown on your computer screen. We encourage you to answer the evaluation and give us feedback, as we always try to listen to the feedback and improve our webcasts. And now with that, we have very few minutes left for a couple questions. There was just really a lot of interest. I guess we had a question. We talked about the difference between MapShed and Model My Watershed, and someone asked also, what's the difference between that and basins? And maybe Barry or Anthony, you want to answer?
Yeah, let me take a quick stab at that. Basins at this point, unless it's changed since I last looked at it, really is not a fully enabled, web-enabled application. You can download data and run it on your desktop, but in this case, Model My Watershed, everything is running on the web, absolutely everything. All the data is on the web, models and everything. So that's the primary difference.
Okay, thank you. There was questions about costs. Is there costs for anybody to use these two tools for MapShed or Model My Watershed?
Presently, the use is completely free. It's supported by projects. We basically take a surcharge from each project for developing new features and use that to support the platform. We may have to think about other ways to keep the lights on. Our Amazon costs are are real, on the order of $20,000 a year at this point, but quite manageable. Maybe we'll have donations, maybe we'll have licenses for users who use the site very, very frequently, maybe frequent users, like with Google Drive or Dropbox, you get a certain amount for free and then you have to pay for more. We're going to try to keep all the features available to everybody for free so that public users and students and people who are, and NGOs can use it as a learning tool.
Okay. With that, I know there are costs, but then we're asking you also, there's interest in whether there's any plan to add other environmental measures besides nutrients and sediment.
Absolutely. On the list of models that I had listed as potential possibilities, one of them that we're really very interested in is ecosystem services or natural capital. Things like, well, if you're planting a forest or putting in buffer strips, what are the benefits for carbon sequestration or for biodiversity? And there are models that have been developed by organizations like the Natural Capital Project Organization, Stanford, University of Minnesota, the Nature Conservancy, and World Wildlife Fund are partnered in that. And they've got some great open source modeling packages that we've discussed incorporating. There are lots of possibilities for adding other models.
Okay, thank you. I apologize, we have not been able to get to all the questions, but the contact information is up on the screen. So if your question didn't get asked, please do contact the speakers. They've been very gracious in offering their time. I think willing to talk to you further also through email or otherwise. But at this time, I'd like to conclude today's webcast. Thank you all of our amazing speakers, and of course, thanks to everyone who joined us. That ends our webcast for today. Thank you again for joining us.